Okay, I think we can start. So welcome everybody to the, I think, fifth PrimaVera colloquium. And apologies that the announcement was sent around so late. So there were some problems attached, but this has now been resolved. In 2 weeks, there will be a talk by Stella Capodistria on integrated learning and decision making. So we know that already. So we will send out the invitation very soon. And today we're happy that Tom Heskes will give a talk on causal inference and discovery. So Tom, please go ahead.
Okay, thank you, Niels. Yeah, so thanks for inviting me and thank you for joining on this kind of warm day. So what we'll do, so maybe first a disclaimer, I'm not really into predictive maintenance, right? So my background is really machine learning. I will be talking today mainly about causal inference and discovery. But when I look around for predictive maintenance is all about, we had many talks when preparing the proposal and discussing what might be interesting topics, and some of them I may know something about. I realized that there is also a type of maintenance which is called prescriptive maintenance, which is perhaps even more cool because that's really related to kind of a causal notion. So when I found this image here on different maintenance strategies, I was hoping that maybe in 5 years we could submit another proposal doing prescriptive maintenance, but I'm also hoping that we can all do a bit of prescriptive maintenance in the context, of course, of PrimaVera. But like I said, I mean, my main background is in machine learning, and the main applications that we have been working on, in particular when it comes to causal inference and causal discovery, has been in healthcare. So some of the examples that I will show are on healthcare, and I hope that you yourself can try and make the translation to predictive maintenance, because whether it's about health of people or health of machines, I mean, it's not that different. Okay, so this is, I guess, a clear-cut case of where there is a causal relationship, right? And we kind of know that. So smoking is not good for your health, and it increases the risk of lung cancer. And there was this nice graph here on the right-hand side. It shows the tobacco consumption in different countries, and then on the other axis, the incidence of lung cancer. And you can see that there is a clear correlation between the two, right? So we have a correlation, and we kind of understand what's going on there. So we expect there to be a causal relationship as well. Then already quite some years ago, but still it's quite interesting. This is a similar graph, not about smoking and lung cancer, but about chocolate consumption and Nobel Prizes. And this is also in different countries. And what you can see here is that the correlation is in fact a lot stronger than what we saw for smoking and lung cancer. And this was published in one of the main medicine journals. And there were lots of jokes around that, right? Like Nobel Prize winners saying, yeah, indeed, I eat a lot of chocolate and things like that. I guess, I hope you understand that there is probably not a direct causal link between chocolate consumption and winning Nobel Prizes, right? So that's then also the claim and the most important claim of the particular paper, right? So be careful, correlation is not causation.
Tom, there's a question.
Oh, yeah.
By Stefan. It says the R equals 0.22 is not so strong, question mark.
Yeah, indeed, it's not so strong. And here it's a lot stronger. I think it's 0.7. So even though in this case, the R is not so high, there is a clear causal relationship. And it's definitely a significant one right here. So even though it's low, it's clearly significant. We can also kind of understand it. Here, it's even higher. It's definitely a significant correlation. But yeah, what's the causal relationship here? Right? Then this is not a real data set, but it's good to think about it, right? So here, suppose that you have a data set on car accidents, and so there is speed in there whether it was slippery, yes or no, and whether the car driver was actually heavily braking. Right? So probably what you will find in this data set that when a car driver is actually heavily braking, there is a positive correlation to actually crashing. Right? So if you model this as a regression problem or a classification problem or whatever, then you will find this kind of positive, strong, probably positive link between braking and crashing. And if you really try to interpret that as a causal relationship, well, you're doing the wrong thing, right? And I guess something similar will happen with machines and controllers, right? So when they feel that things might go on, they try to turn the knobs and try to change that, but it might not work anymore. Right? So then you find a positive correlation between something going wrong and changing the knobs, but actually the causal relationship still, hopefully, it's kind of a negative one, right? So braking definitely helps. And this is really the kind of fundamental difference between correlations that describe the world as we actually observe it and causal relations, right? So they try to predict how the world will change when we manipulate it or when we intervene, when we do interventions. And the goal now of causal inference and causal discovery is to try and find those causal relationships from actual data. Okay? So instead of doing statistical inference, I will say a bit more in a minute, where we try to find the correlations and try to make predictions. With causal inference, we try to make predictions of what happens when we intervene. Right? And the language that we tend to use for that, at least in the field that I come from, is with what we call graphical models, right? So we like to think in terms of these kind of graphs here, where you can, for example, show the link between smoking and lung cancer. And then you kind of know that there's something going on there with tar and with radicals. Maybe there is some genetic predisposition. And maybe the model looks a bit like the model, the graphical model on the left-hand side. Well, if we go to chocolate and Nobel Prize winning, then there must be a correlation. So there must also be some causal links there, but not probably, I guess, not directly from chocolate eating to Nobel Prizes, and also not the other way around, that in a country where people win Nobel Prizes, then all of us start eating chocolate a lot or whatever to kind of celebrate. We don't expect such a link to be there. We do expect that there's something like wealth in the country, right? So, and wealth is what we then would call a common confounder here in this case. So if the country is pretty wealthy, then you can spend money on eating chocolate, but you can also spend money on education, on research, and that gives you a higher chance to win Nobel Prize. So that's probably the relationship somehow that might be the cause of this correlation between chocolate and Nobel Prizes. Then if you go to this kind of fake data set on car accidents, then there is a direct negative causal relationship between braking and crashing. But because there is so much confounding of danger and slippery roads and speed and things like that, then the correlation can still be positive, right? So even though we observe in our data a positive correlation, it might be that the actual causal effect, the direct causal effect, is negative. So we have to be very careful. And I guess most people realize that we have to be careful. And then people really love to say things like correlation does not apply causation, or correlation is not causation, and correlation does not prove causation. So this is data from Google Ngrams on books that appeared between 1920 and 2008. And you can see that there is this trend, right? So we really like to say this. And maybe in some cases, as in this kind of funny picture, there is a good reason to say this, but sometimes maybe not. That's what we're heading at here. This is, I guess, still the main popular book on kind of big data and the relevance of big data, and that's a revolution and will change everything and so on. Fine, there's a whole chapter in this book on causality, and the main goal of this chapter is to explain to us that we shouldn't care anymore about causality, right? So in exchange, we just have to look at correlations. We cannot know why anymore, but only what. So, and this, yeah, it's too bad. And so science is aiming to understand why things happen, but hey, with big data, we have to get that. That's basically what the authors are trying to convey in this book. And the question is, of course, do we agree? Or can we do any better? So the logical reasoning seems to be, and this is really in our head, right? So we really always tend to think, oh, correlation does not imply causation. And then we tend to think that it's impossible. If we have purely observational data, so we have these car accidents and lots of data of that, or we have Nobel Prizes chocolate and maybe some more variables that we have measured, that it's impossible to discover a causal relationship. Okay, so maybe think about this for a while, whether you feel that that's indeed the case, because now I'm gonna kind of test Murphy's law, I guess. I'm gonna try to do a Kahoot, so pay attention there and see if you can open the Kahoot.it website. If you know how it works, you can also do it probably on your mobile phone. So this is the question that I want you to think about and to answer. So is it possible to discover a causal relationship from purely observational data? Right? So that's the question that I want to pose here. And I'm just wondering how you feel about it. So let me now try and see if I can end my sharing here, at least for this one. And then go to the Kahoot. So I have to share my screen again. Then pick this one. Share. Can you see the other screen now, the Kahoot?
Yes.
Screen? Okay. Oh, but now I did the wrong ones, but I can play it here. Now, check it. And we're going to do a classic one. So, oh, this is a really annoying sound. Let me do that off. Okay. So now you have to plug in this. So you can go to Kahoot.it and you have to plug in this number there. And I can already see some names coming there. Tito's there. Hi, Tito. It seems to work. And we actually will do this twice, right? So this is the first question. Later during the talk, we have a second one. So you can keep it up and running. Let me check. Did we manage? If not, you may want to raise your hand because otherwise, I guess I can start. Okay, let's see. I think you have 30 seconds for this one, but it's the one that we had before. Let me put it on. Okay, so this is the question. Is it possible to discover causal relationship from purely observational data? Well, no way, right? Could be. Only if you know the causal directions. So you should have information about the causal relationships. Yeah, maybe, but under some assumptions, or a short piece of cake. So still 7 seconds here. So you have to make your choice. Okay, wow. I guess I biased you a bit, right? So 14 of you say, yeah, but under some assumptions. And I think that's the right answer. 4 of you say, only if you know the causal directions. Well, we'll check that later. And, well, short piece of cake. Good luck. I don't know. Could be. Okay, so this is just, I guess, who was the fastest one. Okay, so we'll get back to this. Stop sharing this one and going back to the presentation. Let's see how that works. Presentation is probably here. Sure. Okay, works, right? Okay, so this is still, I'm very happy with this audience because most people feel about you cannot really do this, right? Because correlation doesn't imply causation, so you need to have more information. But it's really a fallacy. So we're so used to thinking about kind of pairs of variables where you just have a single number saying the correlation between smoking and lung cancer is 0.22, or the correlation between Nobel Prizes and chocolate eating is 0.89, or is pretty high. Yeah, of course, from that you cannot derive anything because it's a purely symmetric number. Right? So there's no causal direction that you can ever get from that. But if you have more information, and I will give you some examples later on, then why not, right? So, and of course, you have to make assumptions. So if you do statistics or machine learning or whatever, you have to make some assumptions. You can make them implicitly, and machine learning, we tend to do that. But at the end of the day, we're always making assumptions if we do any kind of statistics. So making, well, maybe some slightly more involved assumptions, I will hopefully be able to convince you that we can discover causal relationships, but maybe I don't have to because most of you already saw it. Okay, so let me try and make this distinction a bit clearer, the distinction between statistical inference and causal inference, right? So statistical inference is what we know, and actually we've seen quite a lot of that in earlier talks and also in the paper that Sahara and Niels wrote and it was sent around. So there they train a deep neural network to detect cracks in images of bridges. So that's a typical case, I would say, of statistical inference. So we have some kind of model, we have data with input-output samples, and we have some background assumptions. Deep neural networks are good representations of those kind of images. And then we have input observations, and then we want to predict, or maybe one input observation, an image, and we want to predict the outcome. Is there a crack, yes or no, right? So this statistical inference. Tito talked about fitting crack depths, I saw, and Fejan talked about prediction of failures with black box techniques, and Marielle talked about learning decision or fault trees from actual data. So those are typical statistical inference problems. If you talk about causal inference, it becomes slightly more complicated, right? So we're still given this set of input-output samples, but maybe in some cases we don't, but in some cases we might have also data that is gathered under different manipulations, right? So that you have, for example, randomized control trials where some people did get the treatment and others did not get the treatment, and we have data in both. Right? So, okay, so there may be some interventions, but in some cases we don't have any intervention. We have to make background assumptions, and then once we have that, we can try and build a model, and then given that model, we can ask ourselves, okay, suppose that we're going to implement this policy, or we can do this, we're going to do this intervention, and we also have some observations there. Can we predict the outcome, right, of the model? And for that, and I use this notation here kind of a bit sloppily, but I hope you understand what I'm saying here. So we're kind of observing the axis, as in the statistical inference case, but we're actually setting the variable m here. And for that, we have one way to kind of do that is using do calculus. So do calculus has been invented by Julia Pearl, and it's a way to try and predict the effect of interventions once you have the model, right? If you have a model, you know the parameters of the model, you can try and apply do calculus to compute the effect of interventions. And that's why we typically decompose this causal inference in these two steps, right? So first step is, okay, we have data, we have samples, and we try to build causal models for that. And then in the second step, given these causal models, we try to apply do calculus or some other calculus to predict the effect of a single manipulation, intervention, and observations that we have to predict the outcome. Right? Okay, so hopefully it's clear the difference a bit between causal inference and statistical inference. So what I'm going to do now is give you some examples of causal inference. And I'll split this up in basically two sets. So one set is doing causal inference where you know the causal structure, right? So that's for those of you, I think there were only a few who said, well, you need to know the causal directions. Perfectly fine. If you know the causal directions, you can still, of course, do causal inference or try to do so. And the second part is, you could say, the slightly more complicated part where we want to do causal discovery, which is essentially doing causal inference without even knowing the causal structure. So it's not just we know the causal structure, estimate parameters, compute the effect of an intervention, but also, well, we just have data, and we don't have any clue maybe about the causal structure. Can we still predict the effect of intervention? Okay, now maybe another disclaimer. I will go pretty high level. so the goal of the next couple of slides is not to give you all the details, because we don't have time for that, but hopefully to give you some pointers of kind of models or ideas that you might find interesting, and then probably have to look into a bit yourself, right? So I just, in this presentation, I just cannot go into too much detail. I just want to give you a bit of a feel of what type of causal inference techniques are around and what they are used for. Okay, so this is, I think, one of the most popular ones these days. It's a combination of random forest that probably most of you know, right? So that's by Leo Byman. So you have many decision trees and a whole ensemble, and you can make predictions. And then there is kind of Julia Pearl with kind of his causal inference and do calculus and so on. Okay? And now with causal forest, what you can do actually is to try and predict the effect of treatment. So that's what it's mostly used for. So think about these randomized control trials that you have in medicine, right? Where some people, so some subjects do get the treatment, and that we indicate with this W here. So then WI is 1. So those are the ones who do get the treatment. And then there are also subjects that do not get the treatment, right? So we have these two different sets. And then, well, each subject also has characteristics like age or health status or whatever measurements you can think, right? So those are in these observations here. And even whether or not you're gonna give a treatment to a particular person might depend on these observations, right? So this is kind of the causal model that's behind this. In this case, we're assuming that we measure all the relevant variables. There's no confounding, so we're making quite strong assumptions. But when we do that, we can use kind of random forest, but then with some adaptations, some pretty clever ones, I guess, to kind of learn these so-called causal forests, and then use them to compute for an individual with a particular X, what the average treatment effect for that particular, well, what the expected treatment effect for that particular person with characteristics X would be. And the main trick is here that, well, the complication, I should probably first say, is that for every person, we just have either that they are treated, they got the treatment, or they didn't get the treatment. We don't have both, right? So that makes it rather complicated. And that's why we have this other framework, which is called potential outcomes, because we have to somehow try to predict the outcome for someone who didn't get the treatment. What would happen if this person would get the treatment, right? So you can also view it as a kind of missing variable problem, or, well, there are definitely many different ways of looking at it. So, but the trick here is that the underlying assumption is that all people that end up in the same leaf of this decision tree that makes up this ensemble of all the decision trees in this random causal forest, that they should be treated more or less the same way, that they will have more or less the same behavior, right? And so that's why we have here the sum over all the data points that end up at the same leaf, and then we just have to count the ones that were treated, and then count the effect for those, and the ones that were not treated, and then we look at the difference, right? And this is kind of the average of all of those that end up at the same leaf as X. Right, so that's basically the main idea, but there are some tricks behind it that you can look up if you're interested. So this is now a very popular method for computing treatment effect. Okay, so this is one example. So this is a paper that I really like, and not just since a couple of weeks, but since it appeared like 3 years ago. So this is about fairness, and of course it's an extremely hot topic these days with racism and Freud and so on. It's a very complicated topic, and when you think about fairness, there are at least 20 different definitions of fairness in the machine learning literature. So it's an extremely complicated topic to really discuss, right? But if you would ask me, then this is, to me at least, the best way to think about fairness, and that's called counterfactual fairness, which is a bit related to what I just said. Is that so if we think about black and white persons here, in this case, it is an actual data set. I will say a bit more about that in a minute. So then when someone gets arrested, you don't know, right, what would have happened if that particular person was not black, but was in fact, counterfactually, whether that person was white. Would he also have been arrested then, right? So those are the questions that you have to try and answer. And those are not easy questions to answer and very difficult to answer in individual cases. But when you have a lot of data and when you can do statistics and when you're willing to think about these issues in terms of a kind of a causal language and willing to think of causal models that might explain what's going on, then you can analyze those data sets. And this data set that's also in this paper here, it's a data set on arrests in New York, where it's a quite large data set, I think about 2,000 to 3,000 different arrests, white people, black, Hispanic people, others. And the model that they assumed was something like this here on the right-hand side, where they assumed that there is a latent variable, so something that we do not really observe, but that might have an effect on other variables, namely whether a person is criminal, yes or no, or maybe how criminal a particular person is. That relates to whether this person is carrying a weapon, yes or no. So that is what you can observe, and it's actually in the data set. And then there were variables that relate to what the actual police agent did, right? So was this person arrested? Was it searched? Was it frisked? And was force applied in this particular arrest? And that might depend on race, right? So it might be that this police agent took race into account, and then the arrest became more likely or less likely. So once you're willing to assume such a model, then using this kind of causal inference, using causal inference techniques and counterfactual analysis, you can analyze this data and you can check for yourself whether the police was kind of racist, yes or no, right? So it's hard to do that in individual cases, but you can do it by analyzing kind of lots of data and then doing statistics. And so here the outcome, if you assume this model and if you analyze the data properly, the outcome was that the New York police, in this case, assuming this model, so be careful, did arrest did arrest black Hispanic people, relatively speaking, more often than white people, assuming that they would have the same criminal behavior, right? So the same level of criminal behavior. And it was in particular striking inside the two circles. Right? So in this yellow area here and in this purple area. Of course, it's difficult to see, but you might want to look into the paper. I spend a bit more time on this because it's a hot topic and to show you what you can do if you're willing to apply causal inference compared to kind of standard statistical. Okay, next example, because this is some of my own recent work. So if you're interested in explainable AI, which is another hot topic these days, then there was one method which became really popular in the last 3 years, and it's called Shapley values. I guess by now it's the state-of-the-art approach for explaining individual predictions of complex black box machine learning models that you also saw in some of the earlier presentations. So what they try to do is that for every individual prediction, they try to say, for example, well, the model predicts that you're gonna lend out in this particular data set 5,000 bikes, and then 4,000 of those are due to temperature, maybe minus 20 because of the wind speed, plus 1,000 because of season, and so on. Right? So you really try to kind of break up the prediction into contributions to the different features that are used as input to your model. Okay, so that's what Shapley values do. It's really nice. It's based on game theory. There are kind of these nice properties around that. However, the standard ones, they assume that the model inputs are all independent, right? So they compute the Shapley values, these contributions to the predictions, under the assumption that, well, weather is not related to season, for example. Well, if you go outside, you know that this is weather that's typical for June and July, but not for the winter. Right? So there is a causal relationship there, and you can try and take that into account. And that's essentially what we did when we, you could say, invented the causal Shapley values. that aim to explain kind of model predictions by looking at the total effect that each input has on the prediction of the model. And for this data set, which is about the bike shares, right? So how many bikes are lent out on each particular day. If you consider the model predictions, then they directly depend heavily on temperature, because with temperature, you can also model season, right? So that's why if you think about what the input of the features is, and if you think about the model and the direct effects, then temperature has a strong direct effect on the model output. However, if you think about total effect, then temperature, of course, strongly depends on season. And if you want to take that into account, and that's more closely related to how humans typically attribute cause to observations that they make, then you want to put more emphasis also on kind of seasonal variables that basically capture the difference between summer and winter. And that's what these causal Shapley values do, whereas the standard Shapley values don't have this kind of causal way of thinking, which is in fact a pity, because explanation is really about why things are going on. Right? So with causal Shapley values, we try to incorporate that. Okay, then this one, now I have to be really careful, because this is in fact Marielle's work together with Nauta and Donia Bukur. So this is LIFT, which is an algorithm for learning fault trees from observational data. And Marielle, feel free to interrupt me if I'm saying wrong things here. So the goal of that method is really to find the causal chain of events leading to a global system failure. Okay? And so there is such a model on the right-hand side. So the system failure is T, and then there are events F, G, C, D, E, A, B. There are some underlying assumptions that you have to apply when you want to do any causal inference. And in this case, it seems that the underlying assumptions are that there are causal relationships between these events, right? And there are no common confounders, as in the case of chocolate and Nobel Prizes. And another, you could say, assumption or part of the algorithm is that it then tries to find kind of the strongest direct associations using a particular test, right? And it's called the Montan-Hansel test that I will get back to later on, because we use it ourselves as well for something related. And then it kind of searches for that, and then it finds these kind of models that can be given a causal interpretation in the sense of being a causal chain of events that leads to a particular failure. Okay, I hope I did well here, Marianne. So I wasn't sure where to put this particular algorithm, because to some extent it's also a causal discovery. And causal discovery, there you assume that you maybe know something about the causal structure, but not everything, right? So I put here unknown, but to make it a bit more black and white. But typically you assume maybe some knowledge, but not the complete knowledge about the causal structure. And is it still possible then to say something about causal effects or causal directions? So causal discovery is still causal inference, but then inferring the structure of causal models, right? So really focusing on this first step. So what are the causal models that might explain my data? And typically we do this from purely observational data, and we still have to be very careful. So you can apply it, but you shouldn't really use this for kind of confirmatory data analysis, but more for exploratory data analysis, right? So you can apply it, and then you can say, okay, so I find a causal relationship here. Maybe that's something to dig into a bit deeper, right? I never wrote, hopefully, any paper where I said, okay, so I applied causal discovery, and now I'm sure that there is this causal relationship, because we're not at that level yet with these kind of algorithms. Yeah, so how can you get to this causal information? Well, I guess there are many types, but the three main types that I see are using higher order statistics. So I'll give you some examples of those. Using multiple variables. So even if you look at correlations, but you have correlations not between two variables, but between maybe 10 or maybe even more. It can already start with 3 actually. And use then conditional dependencies, independencies. You can say something about causal relationships. And there's temporal data. And then you go to methods like transfer entropy or Granger coefficient. Okay, so first the causal pairs. So, so this is again a fake example, but kind of interesting, I guess, and we'll go to a Kahoot. to see how you feel about this. And so we're giving, in this case, we're giving two variables, x and y, and nothing else. I'm going to tell you that I know that it's either x causes y or y causes x, right? So there is no confounding. There are no other variables involved. It's one or the other, right? So I know that it's one or the other, and I have to decide. So I have to say, based on this data, right? So the data is the same. I just turned the graph, right? So based on this data, I have to say, what's more likely? X causes y or y causes x, okay? So let's see how you feel about this by going again to the Kahoot. So now I have to stop sharing this one. And I can see if you're still from there. Stop this one. I go back to the Zoom. And now I have to share my screen again, and I'm going to share this one. Can you see the screen?
No.
We're going to go next. So this is the next question. Which one is more likely? Same as on the graph. So x causes y or y causes x. You have four options.
Tom, we don't see a screen.
Either x causes y causes x. They're just as likely, or it's impossible to tell. So note that these are two different statements, right? So one is it's 50-50. I'm sure it's 50-50. And the other one is, well, whatever you're going to say, you cannot really make any claim. This is not working, right? I only have one answer.
Tom, can you hear me?
Was I too fast?
So at least I don't see a screen.
Should I try it again?
Yes, please.
Can you give the number for the Kahoot again?
Or did I lose everyone?
So I just see you. I don't see a screen.
Niels, did it work, or you don't know? Oh, you can't see the options. That's weird. Okay, so let me try again. So this is kind of Murphy's law, right? So, oh, I can see it. So I did see it here. Okay, I'm gonna try again. Okay. I'm gonna exit the game. Okay, so we're gonna have a different pin this time, and I'm gonna share this one. Is this better?
Yes.
So you have to enter again, different pin number. Okay, there you are. Gives me some time for a break here. I didn't tell you the answer, right? Because otherwise it makes no sense. Okay, I guess we're all there, right? 23 sounds a good number, 24. Yeah, we're there, we're there. Okay, I'm gonna start. So we will have the first question again, but I'm gonna quickly skip that one. I think I can do that. Okay, skip. Oh, very good. Next, oh, Tito, you were correct. Okay, then we're gonna go to the next question. So we have these two different options. X causes Y. Yeah, you can see it, right? Yeah, I can see some more answers coming in. X causes Y, Y causes X. Just as likely, impossible to tell. Okay, wow. This is interesting. So most people think they're just as likely, which is nice. Some people say X causes Y, which is what I guess is more likely, but it depends, so that's fine. I would expect more impossible to tell, which is also, I guess, fine. Yeah, so let's see. I can stop share this now, and share the screen again. Okay, so let's see again. So this is what I would say, right? So the point is, if I look at Y as a function of X, it's relatively easy to think of a model that explains this, right? So I can think of just a linear model with additive noise, simple model. If I want to explain the other one, X is a function of Y, yeah, I can do that, definitely, I can. So I can come up with a model that explains that Y changes and then X also changes. But in particular here, and here, it's a bit harder to explain what's going on, right? So there should be some kind of weird cutoff, and the distribution is a bit different, and it's not so easy. So this is what we would say kind of simple model. Y is just a function of X plus additive noise, and this, well, we can make it, definitely, but it's a quite complicated model, right? And if we feel that Occam's razor makes sense, and that's what we typically use if we do some kind of model selection, right? Then we prefer the simpler models over the more difficult ones. Then I think there is reason to believe that this one is more likely than this one. If you say, no, I can make a simple model that does this, then it's of course also fine, but I don't know. Right? So, and you can say, well, this is just a fake example, but you can also think about real world pairs and real world cause-effect pairs. Not so easy, but in particular, the group in Tübingen gathered about 100 of those pairs and competitions on this. There was, since last year, another website called Me that you might want to have a look at. There are really nice data sets there. And this is one example of an actual data set. So this is the altitude of the weather station in Germany. And this is the average temperature over the year, right? Oh, well, over 30 years, actually. And then probably you will agree with me that the causal link goes from the altitude to the temperature. Right, so if you put the weather station higher up the mountain, then it's probably getting colder again. Right, so that I guess, and not the other way around. That if you start heating the weather station, it starts flying or whatever. Or I don't know what causal reasoning we would like to apply there. So I guess we can be pretty sure that the causal direction is from altitude to temperature, and then you can apply your methods and you can see if you also find that. I think currently, kind of, if you look at these types of competitions, then the best methods have like 80% correct. And they're all kind of based on the same idea. You try to model Y as a function of X, you try to model X as a function of Y, and you pick the one which is kind of the simples, the kind of simplest model, and that's probably then the causal direction. Now, you can agree with me whether that's a good way to do it or not. I don't mind, but at least you do 80% correct, right? So it doesn't seem to be random here. So this is the case of pairwise variables, and what you have to do, of course, you have to use higher order statistics. You cannot say the correlation is this, because that's completely symmetric. You have to do something which is asymmetric. So modeling Y as a function of X, or modeling X as a function of Y. This is kind of an asymmetric thing to do. If you have more than two variables, you don't even have to kind of do that, right? Because you can already bring in symmetry by looking at kind of correlations between three different variables. So this is what we do in what we call constraint-based causal discovery. So there we assume that we have lots of variables, maybe 5 in this case. Then we have a whole data set with observations on those variables. And then we still want to do kind of predicting the effect of intervention. Right? So what if we kind of change one of these variables, what's going to be the effect on other variables? And again, I have to go a bit fast here and cannot really go into detail also because of time. But the reasoning goes a bit as follows. So if you give me a causal graph, right? So you tell me, okay, these are the nodes and these are the causal links. then I can derive kind of independencies, dependencies, in particular conditional independencies and dependencies for this particular model. Okay. And now what we have to do, if we want to do inference, we have to reason backwards. So now based on data, we might be able to find on conditional dependencies, conditional independencies, and then we try to reason backwards to kind of which causal models, which causal graphs correspond to this particular set of conditional dependencies, independencies that we have. Okay, so that's kind of what the reasoning that you can apply. It turns out that actually you only need two relatively simple rules, and then you have almost everything. And the rule is something like this. So if you find a particular variable that breaks the dependency between two other variables, then you know that there must be a causal relationship from this particular variable that breaks a relationship to one of the two variables or to both. And here's an example. So suppose that you have a party, you drink heavily, you get a hangover, right? So, and then you have a whole data set with lots of parties and lots of drinking heavily and maybe sometimes not, and sometimes you have a hangover, sometimes you don't, and so on, right? So you have this whole data set. Well, in this case, you might find that party and hangover are definitely dependent, but when you start conditioning on whether you drank heavily or not, they become independent variables, right? So if you look at all those nights where you drank heavily, then it didn't matter whether there was a party, yes or no. You just had a hangover, or it was very likely that you had a hangover, right? So that kind of breaks the dependency. So if you have something like that, then there must be in your causal graph a link either from drinking heavily to hangover or from drinking heavily to party. So we don't have full information here, but if we observe this conditional independence, we have some information about the causal graphs that may explain this conditional independence. So this is one rule. The other rule is just the negation of that. So when you find a particular variable that makes two variables that were independent, makes them dependent, then you have the opposite. So then there cannot be a causal link in this causal graph. Right? And here's an example of that. It's called the V structure, also called explaining away for those of you who know a bit about Bayesian networks. So it's relatively simple. And if you now try to find in your data, try to search in your data set for these kind of conditional independencies and conditional dependencies, and you find some, then you can basically write down the causal relationships that you must have in your data, in your protocol. So that's the basic idea. And then you can also, of course, use simple rules like if x causes y and y causes z, then x causes z, and like that. You can assume, but you don't really have to, but you can assume that the model has to be acyclic and cycles in there, and then you basically have an algorithm. So this is what the algorithm does if you have a fake model. So suppose that the left-hand side is your model. Okay? So you don't really know that, but it's kind of an oracle, you could say. So it's a true underlying causal structure. And then you have lots and lots of data. And you can do all kinds of conditional dependence, independence testing, anything you like. Okay? And the model that you can get back, basically, and that's why I said on one of the slides, I said sets of causal models, is in fact this one, on the right-hand side, right? So, so for example, here between A and C, in the actual model, we were assuming that there is a confounder. I cannot find it back in this case. So I can find in this case that C cannot cause A, but I don't know whether this is a tail, meaning that A causes C, or whether it's an arrow, whether there's a confounder between A and C. So this could be chocolate and this could be Nobel Prizes, for example. Okay? So I can't really tell. So this is the correlation, is not causation, right? So if I would just have these two variables, I would have can tell here and I would have can tell here. But because I have more variables and I can look at conditional independencies, conditional dependencies, there is more that I can tell. And this is a case where I can actually tell quite a lot, and I can reconstruct basically many of these links, these causal links that are in this particular unknown graph, and I can find them back if I have data, and I can do this kind of conditional independence and dependence tests. Okay. So that's the idea, and we applied it actually quite a lot to do exploratory data analysis on medical data sets. And this is the one where I think we were most successful. It's data and actually the different data sets on ADHD. So ADHD is attention deficit hyperactivity disorder. There are basically two types of symptoms, which is why you have this kind of complicated name. One is related to inattention and concentration. The other one is related to hyperactivity and impulsivity. And it's known that it depends also very much on genetics, right? So if your parents have ADHD, then you're more likely to have ADHD as well. And also boys tend to have it more than girls. So what you can then try and do is look for conditional dependencies, independencies. And in fact, in all the data sets that we had, and we had 3 different ones, completely different populations, we always found this conditional independence between gender and hyperactivity conditioned upon inattention. So inattention is kind of breaking the dependency between gender and hyperactivity. So independence or inattention must be somewhere in between, right? And since inattention cannot really cause gender, right? Makes no sense. It must be that inattention causes hyperactivity. Of course, if you're willing to make all these assumptions that you have to make if you want to do causal discovery, right? So it gives a suggestion that the link might be there. And if you now want to think of a therapy, then I would say, well, try to focus on finding a therapy for inattention, because then you might also help hyperactivity. Whereas the other way around, if you solve on hyperactivity, it probably doesn't really do anything with inattention. Right? So that's kind of the claims that we can then try and make. Okay, so this is the causal model that the data basically suggests, and with that you can make it even into a new print now. So this was from a couple of years ago. Okay, you can do this with more variables. So this is more data on the comorbidity between autism and ADHD, and then you have more interesting relationships. But the one that we found in all these data sets is still there. As you can see here, gender, inattention, hyperactivity. So that's, and we've also ways to kind of give more confidence, right? So whether links are likely or maybe, well, you don't really know. So maybe 52% here, but this is a very likely link. Very okay, then maybe the last one before I'm gonna finish up is time series data. So this is actually work with Errol, who's also here. So again, I apologize if I don't explain it well. So this is ASML, having lots of huge machines there, of course. Many things can go wrong. There are many variables, many different sensors. Time scales going from nanoseconds to days, orders of magnitudes. And the method that Errol came up with is to apply transfer entropy, which is essentially trying to find causal effects between pairs of variables, looking at the time scale, right? It's a bit related to Granger causality for those of you who have heard about that. So you can try and do that, but then you have, well, a relationship between pairs of variables that might be connected, but it's still kind of a mess. So then on top of that, you can do graph analysis, a bit similar to the causal discovery method that I just explained, to try and find the most influential nodes, which is very relevant, of course, for root cause analysis. So some people might say, well, this is not really causal discovery because we're using kind of more we're using the direction of time more than really causal relationships, and you have to be a bit careful, right? So the standard example is that the rooster always crows before the sun rises, but there is no causal relationship between the rooster and the sun going to rise, right? So even though it happened before, there is not a causal relationship there. So we have to be a bit careful here, but I think in particular for these kind of huge machines, I mean, these are the methods that you have to apply to make some kind of, to find some kind of structure in this, you could say, chaos there. And there was really interesting work going on. Maybe Stella is even going to say a bit more about that next week, because the people at the TU, Alessandro and master students are also involved here. So this is really cool and really worthwhile to pursue. Okay, so let me try and finish up here. So I hope I've convinced you that this is a really interesting field to work in. So going all the way back to philosophy, right? Is it even possible to infer a causal relationship from purely observational data? Then there was Julia Pearl with his kind of do calculus and Bayesian networks and so on, graphical models. But I mean, what's also really nice is that nowadays we have these packages, right? So most of the packages are still in R. There are some Python packages, but there's pretty good software that you can really play with and apply to your own data and see what you can get out of that. So that's what I also highly recommend. So if you want some pointers, then let me know. Okay, so this is my take-home message. Of course, we can say correlation is not causation, and we can always say that, and it's perfectly fine if you just have a pair of variables and then you give this symmetric number and you summarize the dependencies. You can write papers on it. It's fine. I don't care, but it's pretty boring and it's not so interesting, I would say. So for me, it's much more interesting to see what we can get out of this data, also in terms of causal relationships. It's not easy. So those of you who said piece of cake, well, good luck. But we can, and I think we should even try, because those are the type of questions that at the end of the day we want to answer. Right? Which knobs do we have to turn to get the effect that we are willing to have? And so this, I guess, is challenging, it's multidisciplinary, exciting opportunities, and it's more the kind of cool part, and hopefully someday it can help us to bring us more from kind of predictive maintenance to even prescriptive maintenance. That's it. Thanks a lot. And now I wonder if there are some questions.
We start the clap first,
Let
right?
me stop share this screen.
Tom, I have a question. Can I?
Sure.
Tito here. Nice talk. Nice to see how you lead these causalities, and well, you might not be surprised, but I'm especially intrigued by the final part. So the automated failure root cause analysis. That is something that I typically do from my material science background. But if that could be supported by data, that would be very nice. Mm-hmm. But I'm wondering what would be the balance or the ratio between the amount of data that you need and the complexity of the type of relations or causal models you could find. Can you say something about that? I can imagine as soon as the model gets a little bit more complex, that would probably require a lot more data. But is that true, or how does it scale?
No, so to be honest, I don't even think so, right? So the examples that I gave, it really helps if you have more variables, because you can look for intricate relationship between those variables. And of course, at some point, you have to be careful that you have enough data to reliably test whether there are conditional dependencies, conditional independencies, and so on. And in the case of information of transfer entropy, so you want to have enough data to check whether two variables are really related, yes or no. So yeah. In some cases, you may have to correct with Bonferroni corrections or things like that, and be a bit more conservative with your statistical tests. It could be, right? But still, I think more variables in general for causal inference helps to find more relationships rather than that it hurts.
Okay.
Also have a question in the same type.
Yeah.
Because in the theory you provided in that last example was if you have infinite data. So my question was, well, how much data do you really need? And let's say in typical model fitting, you have theory is about theoretical identifiability. Yeah? Is a certain model theoretically identifiable, but also practical identifiability? How much data do you need to have a certain, even if something is theoretically identifiable, you must also ensure you have sufficient data with sufficient information content. So those are issues I think would also apply here. But I don't know if there's some theory around that, and also to provide you with some indication of how much data you need and what characteristics are needed.
Yeah.
To infer the causality from the data.
No, definitely. So we actually have some project on that together with Aad van der Vaart, who's really into statistics much more than I am. So there we have this project where we try to find out basically what are the statistical properties that you really need, and in particular in the large sample limit, right? So
yes, yeah.
lots of data, do these algorithms still work? The problem with causal inference, in particular the ones that I described, where you have more variables and you have to look at conditional dependencies, it's a bit weird even, namely that if you have lots and lots of data, then at some point you find even the smallest dependencies and nothing is conditionally independent anymore. And then what can you still do? So yes, those are very relevant questions, and people definitely working on that. My main concern at this point is that the assumption that we then have to make kind of strong statements about whether something is identifiable or whether you really find back the true model in the limit, blah, 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 that those assumptions are rather strict. So you really have to make strong assumptions. For example, that if there was a conditional independence, that there was even kind of a gap. So that it's not kind of, you cannot have kind of weak dependencies, because that's too tricky. You have to have either complete independence or you need at least epsilon dependence, right? So think that, and then you can do the theory. So there are definitely people working on that, but very complicated.
Thanks. Yeah, I can imagine.
I had to mute myself because there's some noise in my background.
Yeah.
Are there any other questions? It seems not. So I guess, Tom, thanks a lot for this very nice talk.
Yeah. Welcome.
It was,
Thanks.
thanks to everybody, especially to me, very, very interesting. And yeah, see you all in 2 weeks. I will send an announcement, or Bridget will, and then we will have a summer break. So stay tuned for the last seminar before the summer break.
Okay.
Goodbye, everybody.
Bye-bye.
Goodbye.